would have been the final week before the final exam previously. So what we'll do is we'll do a review, just go through the 4 chapters, pick out the important parts. Only being 4 chapters, the final test will be specifically pulled out of just Pan Global text. There won't be questions regarding anything in the Herman textbook PowerPoints. So we'll keep it to Pan Global, TSSA type questions, to keep, just so that the studying part under these different circumstances are limited just to 4 Pan Global chapters. Chapter 7, Electrical Theory of DC Machines. DC Machines was going to be the next test that we did, test number 3. So there will definitely be questions on the final test regarding DC motors and generators. Chapter 7 starts out with atomic structure, magnetism, units of electricity, ampere, voltage, resistance, electromagnetic induction, the fact that when current flows through a conductor, there is a magnetic field created around that conductor. The right-hand rule determines the direction of the magnetic field around a conductor. Generator action and motor action. What happens to that conductor in a magnetic field when there is current flowing, or if there's a magnetic field and the conductor is moving. So in motor action, you got the conductor being moved by the magnetic field with current flowing. With generator action, you are moving the magnetic field and creating current flow in the conductor. Chapter 7, Objective 3, Design Operating Principles of Direct Current Machines. The armature conductors, the pole pieces, armature core. Take time and read through, review. The design is DC motor, showing the parts, commutators, and the brushes. The different types of windings, the lap winding and the wave winding are the 2 windings that they describe. There are other ones, but we're not going to worry about those. Torque is produced by the armature conductors in a generator. Opposes the driving torque applied to the generator shaft of the prime mover. The torque increases with load, requiring increased input from the prime mover in order to overcome this low torque. There is a couple calculations that it does show you there. The calculations that we're going to be concerned with as long as you're aware of this type of calculation, if you need to do the calculation, it's important to know where to find that so that you can access it and use it if you have to. We won't worry about a question like this with this formula on the final test. Armature reaction is an important aspect of the DC machines. Armature reaction causes the neutral plane within which the brushes have been placed to shift, so that the brushes are now shorting coils which produce voltage. Heavy sparking occurs at the brushes as a consequence. Sparking can cause damage, and the effects of the armature reaction must be overcome. We did do in the previous class, the previous ELEC 1009 lab was done looking at the effects of armature reaction. That lab, I could make it accessible. It's lab number 24, I think. These self-test problems are good to go through too. Just to review, we haven't gone through them in class, but they are there. They're good to use. Types of DC generators. Three main types: shunt, series, and compound. Shunt is a term which means in electrical that it's in parallel. So the shunt field is in parallel with the armature. The shunt field is always excited when a generator is in operation, whether on a heavy or light load. The series field, on the other hand, is only excited when the machine is delivering a low current. From this, we can see that a series generator will have very low voltage when the machine is at no load, whereas a shunt generator will have fairly constant voltage at all loads. This influences generator operating characteristics. Here it shows a series wound DC generator where the field is in series with the armature, as opposed to shunt where it's in parallel with the armature. Compound wound DC generator has both field in series and in parallel. As we saw in the YouTube video on DC generators, there's usually a switch. The switch changes from series to shunt in a type machine like this, that it operates as a series machine and then switches over to the shunt, so you have both characteristics. One of the most important characteristics of any generator is the variation in its terminal voltage with changing load. Load is the current draw. The voltage change measured between no load and full load is the voltage regulation, or simply regulation, and is determined by experiment for a machine. Percent regulation, you may have a question on this on the final test. It's simply percent regulation is the no load volts minus the full load volts divided by the full load volts. And this is what shows you the differences between the DC machines, the voltage regulation. Generators can be separately excited. Where the excitation voltage comes from a separate DC source. With separately excited generators, the voltage decreases with increase of load current because the armature voltage drop due to armature resistance increases. The armature reaction reduces the effective flux and consequently the EMF. So the voltage regulation curve for the separately excited generator is decent as far as voltage regulation. The separately excited generator has a decided advantage over the self-excited machine because it will operate in a stable condition at any level of field excitation. This characteristic makes it particularly suitable as an exciter for a separately excited generator, or for a central power station alternator. In this plan arrangement, the exciter, the separately excited generator, is driven off the main turbine shaft from the second or pony exciter, which supplies the field of the first. So looking at the different types of generators, with a shunt-wound generator, the terminal voltage decreases with increase of load for the same reasons as a separately excited machine, but the effect is more marked. This is because in this case, the shunt field is weakened by the reduction of generated EMF. The shunt-wound generator voltage curve is shown similar to the curve here. The shunt generator, which is self-excited generator, depends upon the residual magnetism in the field circuit to build up the terminal voltage as the machine is run up. Failure to build up voltage may be due to loss or the reversal of this residual magnetism. Passing current through the field coils can restore the voltage. A 6-volt storage battery is usually sufficient for this purpose. Before deciding to restore the residual magnetism, care should be taken to see that the field circuit is in good working order, since a fault could also prevent voltage buildup. Commutator must be clean, the brush is clean, and the brush connection is good. The field coils should be checked for open circuit and for short circuit. Shunt-wound generators have been used for charging storage batteries. Because the voltage falls off as the current increases, shunt generator applications need to be close to the load. The series wound generator is a self-excited generator which has armature and field connected in series. The initial EMF generated depends on residual magnetism. The field current is also the load current, so that full flux and therefore full voltage cannot be achieved until full load current is flowing. Compound wound generator combines the principles of both shunt and series machines, and it is the design with the most applications. Compound generator can be a short shunt or a long shunt, as shown in figure 31, depending on how the fields are connected. So short shunt, compound wound, your field windings are connected slightly differently. In the short shunt, you have the connection between the two fields before the armature. The long shunt, the connection has series field connected directly to the armature and the shunt field in parallel. The relative strength of shunt and series fields can be chosen so that the regulation curves show rising voltage with load, which is over compounded machine, or falling voltage with load, which is being under compounded machine, or a constant voltage from no load to full load, which is a flat compounded machine. The winding may be connected so the shunt field is in parallel with the armature only. This is called the short shunt. Alternatively, the shunt field may be in parallel with armature and series field. This is called the long shunt. The operating characteristics of both connections are very similar. Compound wound generators are used for railroad power systems, synchronous motor generator units, and as power for large earth-moving equipment. The three factors affecting the electromotive force developed by the generator are the speed in which conductors cut the magnetic lines of force, the strength of the magnetic field, and the number of conductors cutting the magnetic lines of force. An increase in any one of these three factors causes an increase in the electromotive force generated. A constant speed driver drives most generators. The number of conductors on the armature is determined prior to construction and is a fixed quantity as far as the operator of the generator is concerned. Varying the strength of the field controls the output voltage of the DC generator. This is accomplished with a field regulator or rheostat, which controls the current to the field coils. A rheostat, as seen in figure 32, is connected in series with the shunt field and is used to control the current flow through the shunt field, shown in figure 33. A rheostat is a type of variable resistance. It is made up of long resistance wire or coil. Adjusting the movable contact to make the resistance wire longer or shorter varies the resistance. A long resistance wire results in a small current. A shorter length of resistance wire results in larger current flow. So 32, this is a rheostat itself. One terminal here and one there. And the length of the whole resistor is this long, and moving the movable contact adjusts how much of that resistance is put into the circuit. There's the symbol for that adjustable resistance here. As far as generators are concerned, the magnitude of the induced EMF depends mainly on the strength of the magnetic field and the rate at which the flux lines are cut. An increase in load will cause a drop in the terminal voltage, and to counteract this, a field resistance must be reduced. This will allow greater field current flow and increase the flux density. Generated voltage is directly proportional to the rate of cutting the lines of flux. Required movements of the field rheostat may be carried out by hand or may be automatically controlled. Automatic voltage regulators work on the fundamental principle that a terminal voltage change calls for an inverse change in flux. The main difference between a DC motor and a generator lies in the manner in which the machines are operated. The generator converts mechanical energy to electrical energy. The motor converts electrical energy to mechanical energy. There are three general types of DC motors, classified as DC generators, according to the method of field excitation used. The three types are, again, shunt, series, and compound wound motors. They possess certain individual characteristics which depend on the winding. So a shunt motor, similar to the generator, has a field in parallel with the armature. Series motor has a field in series with the armature, and compound has both series and shunt fields. Speed control is easily achieved in all DC motors. Because of this, DC motor drives are preferred to alternating current for many applications. That's not the case anymore with variable frequency drives, as we discussed briefly before the break. Because DC motors require more maintenance, AC motors and variable frequency drives are the more popular choice in this day and age for motor control. DC motors show characteristics regarding starting torque, overload capacity, and speed variation with load changes. In order to measure these, the motor must be run from a supply with constant voltage. It must be borne in mind that these characteristics determined by experiment are the inherent characteristics and do not include any manual adjustments. To select a correct DC motor for a particular application, it is matched with the load requirements of the known motor's operating characteristics. The shunt motor is classed as a constant speed motor. Little change takes place in its speed over the whole range of load. Adjustment of the field rheostat controls the speed. The field circuit should not be open if the motor is running unloaded. The weakening field causes the motor speed to increase. The increase in motor speed can be excessive and dangerous. If the field is disconnected during motor operation, field flux drops to a small residual value and motor speed goes dangerously high with the possibility of damage due to the high centrifugal force produced. A DC motor only takes the amount of current it requires to handle the load it is driving, as the current is very low. In the case of the series motor, load current is also excitation current. Therefore, when the load is very low and the speed is inversely proportional to field flux, the speed can become dangerously high. For this reason, the series motor must never be operated without load. The load is fastened to the motor so that it cannot become disconnected. Direct shaft coupling, chain drive, or geared drives are preferred methods. The torque of the series motor increases as the speed decreases, so it is commonly used with equipment requiring a high starting torque, such as driving electric trains. Series motors are also used for cranes and hoists, where light loads are lifted quickly and heavy loads more slowly. The compound motor combines the characteristics of the series and the shunt motor and takes into account both speed and torque characteristics. The compound motor is used where a fairly constant speed is required together with the ability to handle sudden heavy loads. Here in figure 36 illustrates the speed characteristics of shunt, series, and compound motors of comparable full load speed ratings. And then a summary of different types, operating characteristics of DC motors. With the different types of compounding, cumulative compounding, and differential. The difference is the polarity of the fields that you have connected. So between the two, compound, the cumulative compound is excellent starting torque, good constant speed, and will not run away under no load conditions. The difference compound, very poor starting torque, absolute constant speed under varying flows over a small range. So it has very few applications, probably because of even better characteristics of this type of available in AC motors. So the differential compound isn't, it's an option, but it's not very often used. Speed regulation behaves with respect to load and is termed similar to the generator. Percent speed regulation is no load speed minus full load speed divided by the full load speed times 100%. The smaller the variation in speed between no load and a full load, the better the speed characteristic, and the nearer the speed regulation is to zero. And examples there. Speed control is normally restricted to shunt and compound type motors. Varying the applied voltage or the field flux alters the speed of the DC motor. To control field flux, a regulating rheostat is inserted in the shunt field circuit, so resistance can be increased, thus reducing excitation current and flux and increasing speed. Such control is called above base speed control. Speeds below base speed are obtained by reducing the voltage applied to the armature. All forms of speed control of DC motors involve one or both of these methods. Torque produced by a motor is proportional to both field flux and armature current. Speed does affect the value of the armature current. The torque equation for a DC motor can be written with the field flux per pole and Weavers, a constant depending on the armature winding, the armature current, and torque in Newton meters. With the shunt motor torque, because the flux of a shunt motor remains constant unless deliberately altered, its torque is proportional to the armature current. As load is added to the current, increasing the torque until the necessary torque to handle the load is available. Figure 38 illustrates how the torque increases on a linear basis versus armature current. In a series motor, the flux is dependent upon armature current. The torque is proportional to the square of the armature current until the voltage no longer increases. Beyond this maximum voltage, which is voltage saturation, torque is proportional to armature current only. The series motor develops torque for large armature currents. It also runs at low speeds with large armature current. This makes it a suitable motor for starting heavy loads. And compound, again, the torque characteristic of compound motor is a mixture of the shunt and series torque characteristics. The compound motor has a definite no load speed and may be safely operated at no load. Figure 38 compares the three types of motors with the same full load torque. Up to the full load value, the shunt motor has a superior torque characteristic to the compound motor, and the compound motor has a better torque characteristic than a series motor. Compound motors can be designed so that they have some of the good starting torque capabilities of the series machine and some of the speed characteristics of the shunt machine. Stop there. Great. Okay, just briefly, starting DC motors, the counter EMF generated in the armature of the DC motor limits the current. At the moment of starting the motor, this counter EMF is non-existent, and because armature resistance is low, very high starting current will flow. Such a current is unsuitable for many systems, and in addition, the high starting torques produced could seriously damage gears, shafts, and other parts of machinery. DC motors are restricted to a starting current of approximately 150% of full load current. In practice, a series resistor is inserted in the motor circuit to limit the current to about 150% of full load current. The series resistor is removed as the machine accelerates to full speed. Changing the resistance can be manual or automatic. So in order to have this resistance in series with the armature, typical manual DC starter is shown here. This particular model is known as the 3-point starter because it has 3 connection points for line, field, and armature respectively. Line, field, and armature. As soon as the DC supply switch is closed, the movable starting arm is moved to the first stud of the starter. So you move it to here. This completes the field circuit via the low resistance of the holding coil and supplies the armature through the starting resistance. This limits starting current. As the machine accelerates, the counter EMF increases and decreases armature current. The movable starter arm can then be slowly moved over. So you bring it to the next point, decreasing the resistance in the starting circuit until the machine has reached full speed. So as it accelerates, you're going to move this arm across this variable resistance until it's at full speed, and you take the resistance out of the circuit. If the supply is removed with this particular starter, the field becomes open circuited. The holding coil becomes de-energized and the spring returns the arm to the starting position. So when This arm is moved all the way across to here. Once it's to the far right side, it's now being held by this electromagnet, this holding coil. So as long as current is flowing through this electromagnet, the arm is held there magnetically, and then if the power supply is open, no longer electromagnet, spring returns this arm back over here, and everything's back to where it starts again. In automatic starter, the starting procedure is initiated by pressing the start button. The machine is stopped using the stop button. Automatic starting of motors has several advantages over hand control. The settings on the starter can be arranged to give uniform acceleration to the motor run-up, and chances of improper operation which occur under hand control are eliminated. Three types of automatic starters are the counter EMF starters, which are sensitive to voltage and will act to cut out armature resistance in steps as the motor back EMF builds up. Current limit starters measure the amount of armature current and reduce resistance in the circuit as the starting current decreases. Time limit starters operate strictly on a time basis and will cut out armature resistance steps at definite time intervals. Figure 40 shows a wiring diagram for an automatic starter of the counter EMF type with voltage sensitive relays. Relays A, B, and C are connected across the motor terminals where they measure the armature voltage. It will increase as the back EMF builds up. Pressing the start button starts the motor. It energizes the main contactor M, which is here. So you have stop-start circuit with the holding contact here. Stop is normally closed. The overload 9596 is normally closed. So we push the start, energize coil M. These contacts close, and you have your M coil energized. The motor therefore starts with resistances R2, R1, and R3 in series with the armature. As the speed increases, the rising terminal voltage energizes the relays A, B, and C in sequence. Relay A will be energized at about 40% voltage, relay B at 6%, and relay C at 80%. Each relay operates to cut out armature resistance. Relay A closes the contacts AX and energizes the main relay A1. This in turn closes A1X and shorts out R1 section of resistance. When all resistance has been cut out, the motor will run until the stop button is pressed where the contacts of the overload are opened by operation of the overload relay. The motor will stop and will not restart until the starting procedure begins again. So go through the chapter questions. It's a good review of that whole chapter. We'll go through the test options. We've done 2 tests. We didn't do tests 3 and 4. They were to be 4 tests at 10% each, and the final test 70%. 30%, which makes up 70 per test. So the 2 options are the 2 tests that we've done, leave them at 10% each. The remaining 20% of the 2 tests that we didn't do will be added to the final test, making the test worth 50%. That's one option. 2 tests that we've done at 10% each. The final test we're going to do 50%. The other option is to count the two tests that have been done at 20% each and leave the final test at 30%. So I have to know which option you are choosing. I talked over with Ryan, and in light of the circumstances, it gives the student a chance, possibly if the first two tests weren't really as high a mark as you hoped, you can hopefully make it up to 50% for the final test. So I would need confirmation by email from each student separately what they choose for a marking scheme for that final test. Okay, we'll look at AC machines. AC theory and machines. First, two tests were based on basic alternating current. So reviewing, this is chapter 8. The generation of alternating current, sine wave, 360 degrees rotation will give you 360 electrical degrees, making up one cycle, one complete sine wave. Because you are rotating a conductor in that magnetic field, voltage is induced into that conductor, creating alternating current. So that's the basis of the start of your research project, actual generation of electricity on a more complicated scale that moves power. Cycling frequency, passes the conductor across two poles produces one cycle. On the sine wave diagram, this means from 0 through positive maximum, negative maximum, and back to 0. The number of times that this occurs in 1 second determines the frequency in cycles per second or hertz of the generator output. The relationship between the number of poles in the machine and its speed gives the frequency of the supply. That's the frequency equals the poles divided by 2 times the revolution per minute divided by 60 gives you the frequency. In North America, the frequency we have is 60 hertz. In Europe and most of Asia and Africa, you'll find 50 hertz. If an AC voltage is applied to a circuit, it will produce an AC current flow. If the voltage and the current reach their maximum values at the same time, they are said to be in phase. This would be the case in a circuit having only resistance. A sine wave with voltage and current is shown in figure 3a, where they are in phase. When the current reaches maximum later than the voltage, it's said to be lagging current. This would occur in a circuit having an inductive load. An inductive load is usually one containing a coil or coils, very often around a magnetic core, which would be a transformer, a motor, a relay, solenoid, any type of electrical device which operates on electromagnetic induction and has coils of wire. If the current reaches its maximum earlier than the voltage, it is said to be a leading current. This would occur in a circuit having capacitance load. A capacitive load is the opposite of capacitive. Capacitors consist of two conductors separated by an insulating material. They're used in telephone and radio circuits. They're also used in motor circuits, single-phase motors. To help them start and run, capacitors are used in power factor correction in facilities where poor power factor causes higher utility rates. So it's a cost savings if you can correct poor power factor. Three-phase power. A balanced three-phase circuit can be looked upon as a combination of three single-phase circuits as far as the relationships of current, voltage, and power are concerned. In the case of a three-phase alternator, the coil windings are connected in three different groups, one for each phase. In this manner, three different voltages, identical in magnitude, but displaced from each other by 120 degrees are produced. If the coil outputs were connected to separate circuits, each circuit would carry single-phase power. When the three coil connections are connected to the same circuit, it carries all three phases or three-phase power. So you got three separate coils of wire, three separate sine waves, 120 degrees apart. Alternators are generators that produce alternating current. Alternators may be built the same way as a simple loop machine, having a stationary field and rotating conductors. However, it's more practical to build them with a rotating field and stationary conductors. The rotating field is obtained by exciting windings on the rotor with DC power supplied through a pair of slip rings. Small portable alternators use a permanent magnet on the rotor. The stationary conductors are called the stator. The three advantages of an alternator with a rotating field are: brushes and slip rings carry only the excitation current, which has a smaller voltage and amperage than the current supplied by the stator to the output terminals. The size of the rotating mass is reduced. Only one pair of slip rings is required for a three-phase rotating field alternator versus a minimum of 3 rings for a three-phase stationary field alternator. It's easier to insulate the output leads, especially important when operating at high voltages. Talk about capacitive loads and inductive. Again, a capacitor consists of two conductors separated by an insulating material. They're used in telephone and radio circuits. Power companies also use the capacitors to correct the effects of inductive loads. The amount of charge that a capacitor receives for each volt of applied potential is called the capacitance of the capacitor. It's measured in farads, and the symbol is C for capacitance. Capacitive resistance is the opposition of a capacitor or any capacitive circuit to the flow of current. In a capacitive circuit, the current flowing is directly proportional to the capacitance and to the rate at which the applied voltage is changing, which is the frequency. Therefore, if either the frequency increases or the capacitance increases, the current flow increases. The vector representation of voltage and currents given in Figure 3a showed that current and voltage in a purely resistive circuit are in phase of each other. The voltage required to overcome the resistance is calculated V equals I times R. This is often referred to as the voltage drop. In the capacitive circuit, it was a leading current, which would be this one. When a conductor moves relative to a magnetic field so as to pass through or cut magnetic flux, a voltage or EMF is induced in the conductor. Whether the conductor is stationary and the field moves, the field is stationary and the conductor moves, or if both move, is immaterial as long as a relative movement between field and conductor occurs. When relative movement ceases, production of induced EMF ceases. The process is called electromagnetic induction. When a current is passed through a conductor, a magnetic field consisting of concentric lines of flux is set up around the conductor. When the current is an alternating current, the field also alternates, building up in one direction, then collapsing into the conductor and building up in the opposite direction. Lenz's law is a law of electromagnetic induction. It states the direction of an induced EMF is always such that any current it produces opposes through its magnetic effects the charge inducing the EMF. So if a current is passed through a coil of wire, the magnetic field is building up around each turn of the coil, cuts adjacent turns of the coil, and induces an EMF within them. The total voltage induced in the coil by Lenz's law is a counter EMF within them. The total voltage induced in the coil by Lenz's law is a counter EMF that opposes the voltage applied to the coil. This counter EMF produces an opposition to current flow within the coil, which is known as self-inductance. Self-inductance is an opposition additional to that provided by the resistance of the coil. In DC circuits, self-inductance delays the buildup of current to its maximum value determined by the value of the applied voltage and the coil resistance. Once the current reaches a steady maximum value, no further induction takes place and self-inductance is no longer a factor. When the circuit is open, self-inductance again becomes a factor, this time trying to delay the current collapse. In AC circuits, because of the continually changing current, self-inductance is continually a factor in limiting the current through a coil. Any circuit capable of producing magnetic flux has inductance. In AC circuits, because of continuous changing current, a circuit with inductive load is usually one containing a coil or coils, very often around a magnetic core. Examples are motors, generators, transformer windings. A very long conductor can also have some inductance. An example is a transformer wire. Inductance affects the current flow only when the current is changing in value. In an AC circuit, the current is continuously changing in value 60 times a second. Therefore, a continuous EMF is also generated. The opposition to the current by the inductance is called inductive reactance, which is measured in ohms. Reactance is the combined effect of inductive reactance and capacitive reactance. In an inductive circuit, the voltage drop due to the inductive reactance leads the current by 90%. In a capacitive circuit, the voltage drop due to the capacitive reactance lags the current by 90%. Inductive reactance causes the current to lag the voltage. Capacitive reactance causes the current to lead the voltage. When inductive reactance and capacitive reactance are connected in series, the combined effect is their difference. The equation for reactance is inductive reactance minus capacitive reactance gives you the total reactance. In test number 2, we did a series inductive resistive circuit, calculating inductive reactance, voltage drop across the inductor, voltage drop across the resistor, the current flow through the inductor, the current flow through the resistor, the impedance, total voltage, total current. On the test, again, there will be a resistive inductive series circuit to do those calculations. Impedance, power factor. On test number 2, there were 10 values to calculate. enough information to do those calculations. It'll be a similar circuit, similar calculations, just to review that part. Alternators. Alternating capacity is rated in kVA, kilovolt amps, or MVA, megavolt amps. Also, it can be in kilowatts or megawatts at a specified power factor. So the generator was rated at 125 megavolt amps and 100 megawatts at 0.8 lagging power factor. The maximum continuous rating, expressed in megavolt amps, is based on the nominal values of stator and rotor currents. Neither of these should be exceeded because the additional losses may damage the respective insulating materials. Alternator nameplates also carry voltage, current, frequency, number of phases, and speed ratings. Excitation data is also included. It's stated as field voltage and field amps. AC generators are usually referred to as alternators. Both single-phase and three-phase alternators are manufactured, but the three-phase alternator is far more common in industry. Modern alternators consist of a stator on which the AC voltage-producing windings are placed, and a rotating armature or rotor on which a DC excitation winding is placed. The rotor's DC winding is supplied through the slip rings that produce a magnetic field, which when rotated cuts the stator conductors, inducing an AC voltage within them. The AC winding is a distributed winding. The windings are distributed in slots around the stator, very much like the armature winding of a DC machine. There are two different kinds of rotor, salient pole rotors and cylindrical type rotors. Cylindrical rotors are used on alternators exceeding 1800 RPM. Steam and gas turbine-driven alternators will have cylindrical type rotors, as shown in 10A. Cylindrical. The other type is salient pole. The stator consists of a magnetic steel core built up in laminated sheets. The winding is placed in slots in the core, the same manner as the armature winding of the DC generator. The rotor carries the field winding supplied through brush gear and slip rings. Slow-speed generators not exceeding 1800 RPM, such as those driven by diesel engines or water turbines, have rotors with projecting or salient field poles. A salient pole rotor, which is shown in figure 10B. Figure 11 shows a multi-pole 240 RPM, 2140 kilowatt, 60 hertz Allis-Chalmers generator. Unlike DC generators, alternators must be driven at very definite constant speed. This is the speed that produces the required frequency of power. For example, 60 hertz is required by the power grid. A two-pole machine would have to be run at 3600 RPM. For a single alternator supplying a circuit load, the frequency of that circuit or system will depend entirely upon the alternator speed. If, however, there are a number of alternators running in parallel to supply the system, the speed of each machine will be locked into the system frequency. The system frequency will not vary unless the speed of all machines changes. Again, if an additional alternator is to be switched into the system supply, it must be run up to an exact speed first to correspond with the others. This is termed a synchronous speed. For a 60 hertz frequency system, a two-pole machine has a synchronous speed of 3600 RPM, four-pole machine 1800 RPM, 12-pole 600 RPM, and so on. Again, standard frequency in North American content is 60 hertz. An alternator alternators normally run at 3600 RPM when 2-pole and 1800 when they're 4-pole. The modern turbo alternator is almost without exception a 2-pole design. The lower operating speed with the 4-pole machines is not generally favorable to a high-pressure turbine design, and the unit as a whole is bulkier and more expensive than a 2-pole machine of similar rating. Most development, therefore, has been concentrated on the 2-pole generator design. The common types of prime movers used to drive alternators are steam turbines, gas turbines, steam and diesel engines. The types of alternator employed will be chosen to match the prime mover, and both will be influenced by the required output voltage, and so on. The alternator, illustrated here in Figure 12, is a multi-pole engine type generator typical for use at speeds below 500 RPM. The machine shown has 28 field poles on the revolving rotor and run at 257 RPM to generate 60 Hz. Typical output will be up to 5,000 kVA. Alternators for hydroelectric or diesel engine generating stations are of a low speed, multi-pole type. In most cases, the hydro station type will have the alternator shaft disposed vertically. Those for steam or gas turbine drive are always of the horizontal cylindrical rotor type shown in Figure 10A. Rotor and stator designs are discussed. Review, reading through those. Generator cooling is important to dissipate heat. Hydrogen cooling is common. The use of a closed circuit system of alternator ventilation and cooling suggested the possibility of some other gas in place of air being used as a cooling medium. Air has the advantages of disadvantage of a poor thermal capacity, high density, and the fact that it will support combustion. The gas, which was universally chosen in place of air for alternator cooling, was hydrogen. Hydrogen has outstanding advantages as a cooling medium. It has a high heat transfer coefficient and will therefore absorb and reject heat rapidly. It has a high thermal conductivity and will transmit in the heat rapidly. It has a low density. This requires little power to force it through a fan and offers very little braking effect or windage to the rotating parts of the alternator. The low density gives reduced windage loss. This results in a direct increase in the alternator efficiency of approximately 1%. The specific heat of hydrogen is high enough to compensate for the low density so that it will carry off about the same amount of heat as air for a given quantity of gas. Compared directly with air, the specific heat is 14 times as great, and its density is about 1/14. Its heat transfer coefficient is about 1 1/2 times that of air, and its thermal conductivity 6 times. The higher thermal conductivity and greater heat transfer coefficient of hydrogen both reduce the temperature gradient in an alternator, or conversely permit a greater output to be obtained from the same frame. The increase in output obtained with hydrogen cooling in place of air cooling on any particular machine has been shown to be 20 to 30% based on a hydrogen pressure of 3.5 kPa. A further increase in output may be obtained by raising the pressure of hydrogen in the alternator. Each 7 kPa increase above atmosphere giving about 1% gain in output. Experiments have been carried out with pressures up to 170 kPa, and alternators are regularly operated up to 100 kPa. In addition, the use of hydrogen for cooling brings the following advantages: reduced maintenance because of the gas tight and hence dirt and moisture-proof casing, quieter operation due to the virtual elimination of windage losses, simplified foundation since external fans and coolers are not required. The disadvantages of the added complications of gas control system and shaft sealing devices, and the necessity for a gas tight and explosion safe casing. And the description after describes how, with the use of hydrogen, if maintenance has to be done, you have to displace the hydrogen with CO2. Which is one of the disadvantages. Paralleling alternators. The process of connecting an alternator in parallel with other operating alternators is referred to as synchronizing. The alternator that is being synchronized must meet the following conditions before it can be put into the operating system. The incoming alternator must be the same voltage as the system. Adjust the alternator field rheostat until the terminal voltage matches the system voltage. Alternator frequency and system frequency must be the same. Adjusting the speed of the prime mover controls the alternator frequency. In most cases, this means control of steam supply to the turbine. Its phase sequence must be the same as the system. If the system bus bars are designated red, white, and blue, and the maximum of the voltage waves of the three phases occur in the sequence red, white, blue, then the incoming machine, which is to be connected red to red, blue to blue, etc., must also have voltage maximum occurring in phase sequence red, white, blue. Phase sequence is also referred to as phase rotation. Lamps or a phase rotation meter can check phase sequence. I believe it was lab 35 that I handed out just to show you the process of paralleling alternators. The machine must be in phase with the system. This means that the phase voltage of the alternator must reach its maximum at the same time as the system voltage reaches its maximum. The phase relationship of incoming machine and system requires use of synchronizing device such as an indicator. This may be in the form of a bank of lamps or a synchroscope. Modern large machines will always use a synchroscope because indication by lamps is not accurate. There are two common manual methods of synchronization, the lamp method and the synchroscope method. The synchroscope method is the best, but lamps are cheaper and may be used in emergency and also have definite advantages in checking phase rotation. It goes through the description of the process. Synchroscope is by far better in a manual system. But automatic synchronization is more common. It's becoming common for each generator or power plant to have its own equipment for automatically synchronizing the generator to the power grid. The manual equipment, as described above, is only used as backup. The automatic synchronizing equipment includes speed matching relay, voltage matching relay, a synchronizing relay, auxiliary relays, and transformer relays or switches. The automatic synchronizing equipment is turned on as part of the generating unit startup. As the generator unit reaches its rated speed, the speed matching relay provides raise or lower impulses to the prime mover. This is done to match the generator frequency to the bus or grid frequency. The voltage matching relay matches the generator and bus voltages by sending more or less excitation to the generator. When the generator and bus voltages and frequencies are matched, as determined by the synchronizing relay, the closing impulse is given to the generator breaker to close its contacts. To take an alternator offline in a system involving two or more alternators, the driving torque of the prime move of the alternator to be removed should be reduced until it's supplying zero current to the bus bars. At this point, its main disconnect switch can be opened, disconnecting the machine from the bus bars. The automatic voltage is then reduced to a minimum by means of the field rheostat. and the DC excitation switch is open. The prime mover can now be stopped. We looked at three-phase induction motors, their operation, the types, take a break, and we'll go through those. Okay, we reviewed three-phase induction motors, the types, their operation, their construction. Three-phase induction motors are superior to single-phase motors in a number of respects. They're self-starting, smaller dimensions for a given power rating, with better power factor and higher efficiencies. The stator of the induction motor is identical to that of the three-phase alternator. In the alternator, a magnetic field produced by supplying a rotor with DC current rotates with the rotor and produces three-phase voltages in the stator winding. As in many other electrical devices, this effect is reversible. Supplying a three-phase stator from a three-phase supply causes a rotating field of constant magnitude and constant speed to be produced inside the stator. As the magnetic field rotates, it cuts the conductors of the squirrel cage rotor, inducing currents in the rotor bars, as indicated in Figure 21. These currents in turn produce magnetic fields, which distort the main field. The main field, in attempting to straighten out, tries to push the bars away from the field in the same direction as the field is traveling. Thus, torque is produced, the rotor rotates and tries to attain the same speed as the magnetic field. It can never do this, however, because if it did rotate at the same speed, there would be no relative movement between the rotating field and the rotor bars, hence induction of voltage would cease, rotor current, and therefore torque would cease. The rotor would slow down, and relative movement between the field and rotor would again exist, producing torque. In practice, the rotor always rotates at a slower speed than the field. The difference in speed between the two is called the slip speed. The slip speed is always just enough to produce the necessary voltage and therefore current and torque to satisfy the load on the motor. On Blackboard, the Herman PowerPoints get into this in more detail, possibly making it easier to understand. The most common type of rotor used in induction motors, this is squirrel cage rotor. This rotor consists of heavy copper or aluminum bars, as seen in Figure 22, fitted into slots in the rotor iron. Shorting rings of the same material as the bars connect all the bars together at each end of the rotor. So the end rings are where all these bars are shorted together. All the iron of the magnetic circuit is laminated to minimize eddy currents. Eddy currents cause heat and therefore losses, so the laminations reduce those eddy currents. Figure 23 shows a squirrel cage rotor, and Figure 24 illustrates a three-phase stator. So three-phase rotor and the stator, the stationary part. This motor shown here is a single-phase motor. It has a squirrel cage rotor, stator, but it also shows a starting capacitor, which is necessary because in a single-phase motor you don't have that rotating magnetic field with the three phases. Also in a single-phase motor, it has separate starting windings and run windings. One particular type of three-phase motor is a round rotor induction motor. The stator of a wound rotor motor is identical to that of a normal induction motor. It's constructed of poles and windings. It may be a 2-pole, 4-pole, etc. stator. Most induction motors have distributed windings. If you looked at the stator windings of an induction motor, you could not count the poles with the compact coils of wire. The rotor consists of coils of many turns instead of the heavy bars of the squirrel cage rotor. The ends of the wound rotor winding are connected to slip rings mounted on the rotor shaft. The principle of operation is identical to that of the ordinary induction motor, with an EMF being induced in the rotor by the rotating field produced by the stator winding. The basic construction of a wound rotor induction motor is shown in Figure 26. In any induction motor, in order to develop high starting torque with low starting current, the rotor resistance needs to be high. As the machine speeds up, the resistance of the rotor needs to be reduced in order to maintain a high level of torque. The resistance of a squirrel cage rotor is fixed. A high resistance rotor, which produces a high starting torque, also produces a high slip when fully accelerated. The wound rotor enables external resistance to be inserted into the rotor circuit during starting and gradually taken out as the motor accelerates. This enables a high torque to be maintained during the starting period. Wound rotor motors are also used for speed control, with a higher rotor circuit resistance causing higher slip and therefore a slower motor speed. It is a very inefficient method of speed control due to the heating losses within the rotor circuit resistors, although inexpensive in terms of capital cost equipment. The induction motor is the most commonly used type of AC motor. This is because the design is simple, it's very rugged. It also has very good operating characteristics. Common uses include driving fans, pumps, compressors, or any machine that requires a steady and reliable power source. The wound rotor induction motor is usually used if speed control is needed. It is more expensive to construct, but allows for the varying resistance in the rotor circuit. Induction motors are available in power sizes from small to over 1,000 horsepower. The synchronous motor is identical in construction to the alternator. Any synchronous machine can be run as an alternator or a motor. Both require a DC supply to the rotor. The difference is that the alternator is driven by a prime mover and generates an alternating current in the stator windings. The synchronous motor, on the other hand, has an AC supply connected to the stator windings, as shown here. In the case of a three-phase synchronous motor, a rotating field of constant speed and constant magnitude is produced by the stator windings. Unlike the induction motor rotor, which depends on slip for its torque, the DC rotor field locks in to the rotating field of the stator, causing the rotor to rotate at synchronous speed from no load to full load. The motor field created by the rotor windings locks into the rotating field of the stator windings. The speed of rotation of the field windings is controlled by the frequency of the AC power supply and the number of main stator poles. Figure 28 shows how the rotor is locked in position by the attractive force of the stator field. This motor has a permanent magnet instead of the DC-induced field. This type of synchronous motor is used only for light loads, such as clock motors. Larger synchronous motors used for heavy loads have the power from magnetic poles produced by the DC power. If the synchronous motor is too heavily overloaded, it will not run at reduced speed, as will the induction motor. It simply drops out of synchronism, producing heavy stator currents, which causes circuit protective devices to trip it out of the circuit. One of the main advantages of the synchronous motor is that it can be run at a leading power factor, unlike other motors, which run at a lagging power factor. If an industrial plant has a poor power factor, which is often the case, Due to the number of motor loads with lagging power factors, a penalty is levied by the electrical supply company, causing electrical energy used by the plant to be more expensive. If the DC supply to the synchronous motor in the plant is increased, causing overexcitation and a leading power factor for such motors, this will help to improve the overall power factor, thus decreasing the cost of energy. The construction of a basic synchronous motor is shown and displayed to you in Figure 29. A picture of a synchronous motor rotor is shown in Figure 30. So the salient poles, slip rings for the DC excitation. Unlike the induction motor, the synchronous motor is not self-starting. It cannot be started with both normal AC and DC supplies connected to the stator and rotor windings respectively. Any attempt to do so would produce heavy stator currents which would trip the machine off the line. Synchronous motors are supplied with a special squirrel cage winding called an amortisseur winding or a damper winding, which is fitted into slots in the rotor pole bases. In the synchronous motor, this winding allows the machine to be started as an induction motor either directly across the line. This is done without the DC excitation applied to the rotor and with the rotor winding short-circuited. As the motor accelerates as an induction motor and nears minimum slip, the rotor short circuit is removed and the DC rotor excitation is applied, causing the rotor to pull into synchronously. The amortisseur winding has another advantage when the synchronous machine is run as an alternator or a motor. When the rotor is running at synchronous speed, there is no relative movement between the rotor bars and the flux of the rotating field, so the amortisseur winding has no effect. During sudden changes of load, however, when the rotor tends to slow down or speed up, the amortisseur winding becomes effective and supplies a torque, which counteracts the tendency to change speed. The speed of a squirrel cage induction motor, if the frequency output or frequency of supply is fixed, can only be changed by changing the number of poles. This can be accomplished by using separate windings for each speed or by reconnecting the windings so that all poles become the same polarity. By these means, a squirrel cage motor can be made to operate at any one of several fixed speeds. Pole arrangements of 2, 4, 6, and 8 poles will give synchronous speeds of 3600, 1800, 1200, and 900 RPM from a 60 Hz supply. The actual operating speeds will be slightly less, about 3500, 1750, 1150, and 875 RPM. Motor design will allow the speed range to be made available with either constant power or with constant torque. Induction motors with wound rotors are classified as adjustable speed motors. The winding connections are shown in Figure 31. The variables, starting resistances, or rheostats are used for speed control. Maximum resistance will give the slowest speed. The result is a constant torque, variable speed motor with high starting torque. Prolonged operation at low speeds must be avoided, however, because of danger of overheating. And since the rheostat involves power loss, this method of motor speed control is inefficient. It's normally used as a type of variable speed starter. Variable frequency drives. Many applications that required adjustable or variable speed control used to be limited to DC motor drives. This is no longer true. Modern variable frequency drives are available for AC induction motors from 1 horsepower to over 1,000 horsepower. VFDs are also called AC drives and also inverters. VFDs are static, solid state devices that have lower power conversion losses. As VFDs can control standard induction motors, they can be easily added to an existing system. Modern electronics has reduced the cost of frequency changing equipment to the point where it has become economical to supply a motor with a variable frequency power supply so that the motor speed can be smoothly increased or decreased. An important application of this equipment is the use of variable speed pumps and fans to control flows rather than constant speed pumps and fans in combination with control valves and dampers. The motor drive speed is controlled just fast enough to provide the required flows rather than wasting power by throttling across valves or dampers. In general, the percentage drop in frequency is proportional to the percentage drop in motor speed. For example, an induction motor that rotates at 1725 RPM when supplied with AC power of 60 Hz will operate at 1581 RPM, a reduction of 8.33%, when supplied with an AC power at 55 Hz, a reduction of 8.33%. VFDs are often installed in Motor Control Center or MCC for AC motors. The speed control adjustment can be in the control room, in the MCC, or at the location of the motor. Figure 32 illustrates VFDs take incoming 60 Hz power and convert it to direct current. The DC is then inverted back to AC at a different or required frequency. The inverter can be continuously adjusted to produce the desired frequency output. The AC frequency sets the speed of the AC induction motor. In this way, motor speed can be continuously adjusted. There was a handout that I gave that talked about VFDs that explains in more detail how the AC is changed to DC and then changed again when it's sent to the motor. Other types of starters. Aren't as common anymore because of VFDs. Step starting, an induction motor will take a starting current up to about 6 times its normal full load current when it is started by connecting directly to the source of supply. Such a starting surge can have a number of undesirable effects, causing lights to flicker as a minimum effect, with the possibility of damage to belts, shafts, and gears in more serious cases. To minimize these effects, reduced voltage starting is used in many industrial situations. There are a number of reduced voltage starting methods in use. Some more common ones are line and peak starters, star delta starters, and auto transformer starters. But again, these are being replaced in the field with VFDs. VFDs aren't mechanically operated like these ones. They are becoming less expensive comparably to the other types. As it says, the auto transformer starting isn't expensive method, but capable of giving one of the best starting torque to starting kVA ratios of the starting methods. Procedures to start the motor by connecting to a lower voltage tap on the auto transformer and then switching to full voltage as the machine accelerates towards full speed. Again, VFDs can be sized a size larger than required to accomplish these types of needs also. We don't need to do transformers again. We remembered them the other day. So this review, along with the couple of lectures that were recorded also, should be adequate with reading also through the chapters to prepare for the final test.